Permit me to begin not with mathematics but with discomfort, for it is discomfort that gives birth to physics. Before the so-called twin paradox unsettled the imagination, humanity lived under a quiet, unquestioned belief. Time flows the same for all. It is universal, impartial, and indifferent to motion, whether one sails across the ocean or sits quietly in a study. The seconds tick in faithful obedience to a cosmic metronome. This was the inheritance of Newton, an invisible stage upon which the drama of matter unfolds. Then came the peculiar insistence of light. Experiments suggested that the speed of light, denoted by the symbol c, is constant for all observers, regardless of their motion. From this single stubborn fact emerged a profound restructuring of reality. If light speed is always the same, then space and time themselves must adjust to preserve this constancy. The mathematical whisper of this adjustment appears in what we call the Lorentz factor, written as gamma equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. In symbolic language, it is expressed as gamma equals 1 over the square root of 1 minus v squared over c squared. From this factor arises the famous time dilation relation. The time interval measured by a moving observer equals the stationary time interval divided by gamma. In symbols, this reads, delta t prime equals delta t divided by gamma, but let us not rush ahead. Let us instead build the paradox carefully as one constructs a delicate tower. Imagine two twins. One remains on Earth, comfortably situated in what we might call an inertial frame of reference, a state of uniform motion, or in this case, no significant motion relative to Earth. The other boards a spacecraft capable of traveling at a velocity close to the speed of light. She journeys outward, turns around, and returns. According to the equation I just narrated, delta t prime equals delta t divided by gamma. The moving clock runs slower. That is, for the traveling twin, less time passes compared to the twin on Earth, so when she returns, she is younger. So far, there is no paradox. It is merely a consequence of time dilation. But now comes the itch. From the perspective of the traveling twin, is she not at rest in her spacecraft? Does she not see the Earth receding at high speed? If motion is relative and special relativity insists that it is, then could she not apply the same reasoning? She would calculate gamma in precisely the same way. Gamma equals 1 divided by the square root of 1 minus v squared over c squared, and she would conclude, the Earth twin's clock runs slow. So each twin sees the other aging more slowly. Here lies the tension. If each sees the other aging slowly, how can they disagree when reunited? When they stand face to face again, there can be no ambiguity. One must objectively be younger. The paradox is not born of mathematics. It is born of symmetry. At first glance, the situation appears perfectly balanced. Motion is relative. There is no privileged inertial frame. If all motion is relative, then how can one twin's aging be really slower than the others? This is the illusion, and it is a beautiful one. The symmetry seems airtight. Each twin sees the other moving. Each calculates time dilation using the same formula. Each believes the other should age less. Yet when they reunite, symmetry shatters. Why? The answer hides not in the equation for time dilation, but in the assumptions beneath it. The time dilation formula delta t prime equals delta t divided by gamma applies strictly within inertial frames. Frames moving at constant velocity relative to one another. The twin on Earth remains in a single inertial frame for the duration of the experiment. The traveling twin does not. She departs constant velocity. She turns around acceleration. She returns constant velocity again. At the turnaround, she switches inertial frames. This is the subtle fracture in the symmetry. The Earth twin remains in one continuous inertial frame. The traveler moves between frames, and relativity treats this difference not as trivial, but as decisive. But before we resolve it fully, pause and reflect on the deeper philosophical wound. The paradox feels disturbing because we carry within us an ancient belief that seeing is equivalent to being. If I see your clock slow, then surely your clock must actually be slow in some absolute sense. Relativity denies this comfort. Simultaneity itself becomes relative. What one observer considers now is not the same as another is now when they are in relative motion. The calculation of time dilation depends on how each frame slices spacetime into space and time. These slices differ. Thus, when the traveling twin switches frames during acceleration, her notion of simultaneity shifts. The distant Earth clock's time according to her coordinate system jumps forward during the turnaround, not because Earth suddenly ages rapidly in a physical sense, but because her definition of at the same time changes. The paradox dissolves once we understand that it was never about two observers continuously measuring each other symmetrically. The symmetry was incomplete. It was an assumption smuggled into the setup by intuition. Physics, when honest, is merciless toward intuition. The illusion of symmetry seduces us because the equations appear reversible. If A moves relative to B, then B moves relative to A true. But the full spacetime story includes the path each takes, and these paths are not equivalent. The paradox is therefore not a flaw in relativity. It is a flaw in our expectations. And perhaps that is its greatest gift, for in confronting this illusion, we are forced to relinquish the comforting idea of universal time. We are compelled to see time not as a river flowing identically for all, but as a dimension intertwined with motion, elastic, geometric, inseparable from the path one traces through the cosmos. The paradox is only a paradox if one clings to symmetry where none truly exists, and in that realization one feels not confusion but liberation. Let us now descend from the illusion and place our feet upon firmer ground, the ground of geometry. The second pillar of our understanding is time dilation itself, not as a trick of perspective, not as an optical illusion of clocks, but as a structural feature of spacetime. Before relativity, we believed that time was independent of motion. A second was a second, whether you walked, ran, or sailed among the stars. But the constancy of the speed of light, that quiet, stubborn fact, forced us to reconsider. Imagine a simple clock, not one with gears and springs, but a light clock. Picture two mirrors facing each other, with a pulse of light bouncing between them. Each round trip up and down marks one tick. In its own rest frame, the light travels straight up and straight down. If the mirrors are separated by a distance we may call L, then the light travels a distance of 2L in one tick. Since speed equals distance divided by time, and since the speed of light is c, the time for one tick is simply 2L divided by c. So far, nothing extraordinary. Now let this light clock move sideways with velocity v relative to an observer standing still. From that observer's perspective, the light no longer travels straight up and down, it traces a diagonal path. While it moves upward, the entire apparatus moves sideways. The light must now travel a longer path to reach the opposite mirror. And here is the crucial constraint. The speed of light remains c.it, does not become c plus v.it, does not become c minus v.it, remains c.s. So if the path is longer and the speed is unchanged, the time must increase. The geometry is simple, yet revolutionary. The light's path forms a right triangle. The vertical side represents the mirror separation L. The horizontal side represents how far the clock moves during half a tick, which is velocity times time divided by 2. The hypotenuse is the distance light travels in half a tick, which equals c multiplied by time divided by 2. Applying the Pythagorean theorem, we say the square of c times t over 2 equals the square of L plus the square of v times t over 2. In narrated symbolic form, that becomes c squared multiplied by t squared divided by 4 equals L squared plus v squared multiplied by t squared divided by 4. Now we rearrange this expression. Subtract v squared times t squared divided by 4 from both sides. Factor out t squared divided by 4. We obtain t squared multiplied by c squared minus v squared, all divided by 4, equals L squared. Multiply both sides by 4. Then take the square root. One finds that the moving time t equals 2L divided by the square root of c squared minus v squared. But remember, the proper time, the time measured by the clock at rest, was 2L divided by c, so we compare them. The ratio between the moving time and the proper time becomes 1 over the square root of 1 minus v squared divided by c squared. And this expression 1 divided by the square root of 1 minus v squared over c squared is what we call gamma. Thus we arrive at the essential statement: the time measured in the stationary frame equals gamma multiplied by the proper time, or equivalently, the proper time equals the coordinate time divided by gamma in narration. Delta t prime equals delta t divided by gamma. Notice something profound. Nothing mechanical has happened to the clock. no gears were compressed. No biological processes were altered by friction or strain. The slowing of time is not a physical damage, it is a geometric necessity. The moving clock is not malfunctioning, it is tracing a different path through space-time. In relativity, space and time are not separate arenas. They form a unified fabric space-time. Events are points. Within this four-dimensional continuum, motion through space affects motion through time because they are components of the same structure. One may express this unity through what is called the spacetime interval. It is written as s squared equals c squared t squared minus x squared minus y squared minus z squared. This quantity c squared times time squared minus spatial distance squared remains invariant for all observers, invariant. That is the sacred word. Different observers may disagree on how much time has passed, they may disagree on how much distance was traveled, but when they combine them in this geometric form, the result is the same. The interval is the deeper reality. From this perspective, time dilation is no longer mysterious. It is the natural consequence of preserving the invariance of the space-time interval. If an object moves faster through space, meaning its spatial components increase, then its temporal component must adjust so that the interval remains unchanged, motion through space. Steals from motion through time, or if you prefer poetry, the faster you chase the horizon, the slower you drift into tomorrow. This is not a psychological effect. It is not dependent on observation. It is woven into the structure of reality itself. The Lorentz factor 1 over the square root of 1 minus v squared divided by c squared grows without bound as velocity approaches the speed of light. This means that time dilation becomes extreme. At speeds close to c, gamma becomes very large and proper time shrinks dramatically. If you could travel at 99% of the speed of light, the factor gamma would be approximately 7. 1 year for you would correspond to 7 years for those at rest. At even higher speeds, the difference becomes staggering. Thus, in the twin paradox, the traveling twin does not age less because of illusion or perspective alone. She ages less because her motion through space-time redistributes her trajectory between spatial and temporal directions. In the quiet language of geometry, the conclusion is unavoidable. Time is not universal. Time is personal. It is the length of the path one traces through space-time, and geometry, not perception, decides its measure. Now we approach the delicate hinge upon which the entire twin paradox turns. Until this point, the situation seemed symmetrical. Each twin could accuse the other of moving. Each could compute the Lorentz factor gamma equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared and conclude that the other s clock runs slow. If this were the whole story, we would indeed face contradiction. But physics is not deceived by surface symmetry. The crucial difference lies not in who is moving, but in how they move. One twin remains on Earth, approximately within a single inertial frame, that is, a frame moving at constant velocity without acceleration. The traveling twin does something profoundly different. She accelerates away from Earth, eventually turns around, and accelerates again to return. Acceleration is not merely a detail, it is the fracture in symmetry. An inertial frame is one in which Newton's first law holds in its simplest form: objects in motion remain in motion unless acted upon by a force. Special relativity is constructed upon the equivalence of all inertial frames. The time dilation formula delta t prime equals delta t divided by gamma is valid only when comparing such frames. The Earth twin remains within one inertial frame for the duration of the experiment. The traveler does not. She inhabits one inertial frame while moving outward at constant velocity, then switches to another inertial frame when she turns around, and finally settles back into Earth's frame upon return. The moment of turnaround is the key. Let us imagine the event more carefully. During the outbound journey, the traveling twin considers herself at rest and sees Earth receding. She calculates gamma 1 divided by the square root of 1 minus v squared over c squared and concludes that Earth's clock runs slow, but at the instant she turns around, she must change her state of motion. She must decelerate, reverse velocity, and accelerate in the opposite direction. This is not a trivial bookkeeping change. In relativity, changing velocity means changing reference frames, and changing reference frames means changing one's definition of simultaneity. simultaneity, the idea of what events occur at the same time, is not absolute. It depends on the observer's motion. In special relativity, the transformation between coordinates in different inertial frames is governed by what we call the Lorentz transformation. In narrative form, the new time coordinate equals gamma multiplied by the old time minus velocity times position divided by the speed of light squared. Written symbolically, this reads T prime equals gamma multiplied by the quantity t minus Vx divided by c squared. Notice what appears. Time depends on position, two events that are simultaneous in one frame. Meaning they share the same value of t may not share the same value of t prime in another frame. During the outbound leg, the traveling twin slices spacetime in two nows at a particular angle, determined by her velocity. During the inbound leg, that slicing angle changes. The planes of simultaneity rotate. This rotation produces a startling effect. From the traveler's perspective. At the instant of turnaround, the Earth twin's clock appears to jump forward dramatically. Not because Earth physically ages in a sudden burst, but because the traveling twin's definition of which distant Earth event is simultaneous shifts abruptly. The larger the separation between the twins at turnaround and the higher the velocity, the larger this shift becomes. Thus, the symmetry is broken not by the mere existence of time dilation, but by the change of inertial frames. Let us view this from a deeper geometric perspective. In spacetime, each twin traces a path, what we call a world line. The Earth twin's world line is nearly straight in spacetime coordinates. She remains at approximately the same spatial position while time progresses. The traveling twin's world line consists of two straight segments connected by a bend at the turnaround point. In Minkowski spacetime, the geometric framework of special relativity. The proper time experienced by an observer is given by the integral of the square root of 1 minus velocity squared divided by the speed of light squared, integrated over coordinate time in narrated form. This reads, proper time equals the integral of the square root of 1 minus v squared over c squared. With respect to t, the proper time depends on the path taken through spacetime, and here we encounter a surprising result. In Minkowski geometry, the straight world line between two events maximizes proper time. This is the opposite of what we learn in Euclidean geometry, where the straight line is the shortest distance between 2 points. In spacetime, the straight line, meaning inertial motion without acceleration, yields the greatest aging. Thus, the Earth twin, who follows a straight world line, accumulates more proper time than the traveling twin, whose world line bends. The asymmetry is therefore geometric, not mechanical. It is not the physical sensation of acceleration that causes aging differences. Even if the turnaround were made arbitrarily gentle, the conclusion would remain unchanged. What matters is that one twin follows a single inertial trajectory while the other switches frames. Acceleration exposes the difference, but geometry decides the outcome. The paradox dissolves when we abandon the idea that each sees the other aging slowly is the whole story. That statement is valid only while both remain within fixed inertial frames. The traveling twin does not. There is no contradiction because the situations are not equivalent. The universe is subtle but not inconsistent, and what seemed at first a logical impossibility becomes, upon careful examination, a triumph of spacetime geometry. The symmetry was never complete. It only appeared so to intuition, and intuition, though a precious guide, must sometimes bow before mathematics. Now we arrive at the deepest layer of the matter, the concept that dissolves the paradox not by argument, but by geometry. Proper time. If you remember nothing else from this discussion, remember this. Physics does not ultimately ask, who sees whose clock running slow? It asks, how much time does each observer actually experience along their path through spacetime? That experienced time, the time measured by a clock traveling with the observer, is called proper time. It is not relative in the casual sense. It is personal, intimate, inescapable. In the language of spacetime geometry, the proper time between two events along a world line is given by the integral of the square root of 1 minus velocity squared divided by the speed of light squared, integrated with respect to coordinate time. Narrated clearly, the formula reads, proper time equals the integral of the square root of 1 minus v squared over c squared. With respect to t, this expression contains the entire resolution of the twin paradox. Notice what it says. For every infinitesimal slice of coordinate time, the actual time experienced by the traveler is reduced by the factor square root of 1 minus velocity squared divided by c squared. When velocity is 0, this square root becomes 1. Proper time equals coordinate time. Life proceeds at its maximum rate, but as velocity increases, velocity squared divided by c squared grows. The expression 1 minus v squared over c squared shrinks. Its square root shrinks. Proper time accumulates more slowly. At velocities approaching the speed of light, the factor approaches 0. In principle, though not physically achievable for a massive object if velocity equaled the speed of light, the expression 1 minus v squared over c squared would become 0, and proper time would cease entirely. This is why a photon, traveling at the speed of light, experiences no passage of time between emission and absorption. But that is another story. Let us return to our twins. Each twin begins together at one event, call it departure. Each reunites at another event, call it reunion. These two events are fixed points in spacetime. Between those points, there are infinitely many possible world lines. Each world line corresponds to a different history, a different motion through space and time. Proper time depends on the path. This is the key. In ordinary Euclidean geometry, the straight line between 2 points is the shortest distance, but spacetime does not obey Euclidean rules. It obeys Minkowski geometry. In Minkowski spacetime, the interval between two events is given by the square of the speed of light times time squared minus spatial distance squared, narrated, interval squared equals c squared multiplied by t squared minus x squared minus y squared minus z squared. For time-like separations where one event can causally influence the other, the proper time equals the square root of interval squared divided by c squared. What is astonishing is this. Among all possible time-like paths connecting two events, the straight inertial path yields the greatest proper time, not the least, the greatest. Thus, the twin who remains inertial, the one who does not accelerate, who does not change direction, experiences the maximum aging between departure and reunion. The traveling twin, whose path bends in spacetime due to acceleration and reversal, accumulates less proper time. This is not a matter of perspective. It is not a disagreement about simultaneity. It is a geometric fact. We may calculate it explicitly for a simple case. Suppose the traveling twin moves outward at constant velocity v for a time t according to Earth's clock, then returns at the same velocity for another time t from Earth's perspective. The total elapsed time is 2t from the traveler's perspective. Each leg contributes t multiplied by the square root of 1 minus v squared divided by c squared. So her total proper time equals to t multiplied by the square root of 1 minus v squared over c squared. The Earth twin's proper time is simply 2t. Since the square root of 1 minus v squared divided by c squared is less than 1 for any non-zero velocity, the traveler's total is smaller. There is no paradox because there is no equality to begin with. Each twin's aging is determined by integrating along their own world line. When they reunite, they compare proper times, and these are scalar quantities. They are invariant. All observers agree on their values. One may argue about coordinate times. One may debate simultaneity, but proper time is as objective as the length of a curve in geometry. And this leads us to a profound philosophical shift. Time is not a universal river in which we are all equally immersed. Time is the length of your path through space-time. To move rapidly through space is to tilt your trajectory away from the temporal direction. Part of your motion that might have carried you forward in time is diverted into space. You cannot maximize both. The universe enforces a kind of conservation. The total space-time interval is fixed. How you distribute it between space and time determines how much you age. Thus, the traveling twin does not return younger because of illusion or asymmetry of perception. She returns younger because her chosen path through space-time is shorter in proper time. The paradox evaporates when we recognize that aging is geometric, and in that recognition, something beautiful emerges. We begin to see our lives not merely as sequences of moments, but as curves in a four-dimensional tapestry, each unique, each measurable, each governed by the quiet, elegant structure of space-time itself.